Okay, good morning, good afternoon, and good evening from Helsinki, and welcome to the Pulse of Network webinar series, episode 14. My name is Claus Still, and I'm the CTO of Creanord. And today's topic is how to build outperforming 5G networks. The topic of today is very relevant, as we have many existing 5G networks out there already, and customers are transitioning from 4G to 5G. In a recent study from Ericsson, the Ericsson Mobility Report from November last year, they looked at the mobile data growth to date, and as we can see from the graph on the left, mobile data is still steadily growing at an impressive 40% rate on a year-by-year basis. This growth is fueled by the rollout of the 5G networks, with more customers moving to these new networks that further enables consumption of data by offering significantly faster speeds than before. If we look on the chart on the right, we can see that the 5G is the biggest contributor to the data growth. In fact, in just a few years, all data growth will come from 5G, and 4G and older technologies will start to decline. But where does all this growth come from? The answer is simple: it's video, which is not a surprise, I think, to anyone. Video has for long dominated in data networks, and once the mobile network was fast enough for video with the introduction of 4G, the same has been true for the mobile networks in particular. Ericsson estimates that 71% of the data globally is video today, and expects it to grow to 80% in 2028. As a side note, I can mention that these percentages are much higher in some countries. For instance, in Finland, mobile subscriptions typically have unlimited data plans, so people don't worry about consuming too much data, and thus they watch much more video on their mobile phones. So in fact, one of the Finnish operators have stated that actually their network carries 97% of the data in their network is video, so it can go really high, and the same trend, of course, is in all of the other networks as well. So from this, it's obvious that one of the key factors to consider when building outperforming 5G networks is to understand video. And that's why I want to dive a bit deeper in today's session and look at the characteristics of the video traffic, what it does to the network, and how 5G will affect this behavior. And I will also talk about how you should monitor and manage the performance of the video and of all the other important service classes that you carry on these networks. So the topic today in particular is to look at video and the traffic patterns caused by watching video. We have many different types of videos out there. Social media video is actually surprisingly big part of the video traffic. And the other big part is, of course, streaming media from different providers. Today, I thought I would look particularly on the streaming video class, because that's a good representation of the video in general. And to understand it, we have to look a little bit under hood how adaptive streaming media works. HLS is the major option for adaptive video, and the way adaptive video in general works is that it will segment the video into smaller segments. So I have here an illustration from Wowza, which shows video, and we have three quality streams that you can select from. We have a very low quality stream, a medium stream for 4G networks, and then a high HD level stream, Wi-Fi and 5G networks, and so forth. These three video qualities have been divided into smaller segments of 10 seconds each. So the way the adaptive streaming media works is that when it starts to play the video, it will get a list of all of these segments, and then it will select typically start by selecting the lowest quality video and load the first segment from the lowest quality stream. And when it loads it, it will see how quickly the network can provide that video segment. If the network is fast and it takes a very short time to load that segment, when it needs to play out the next segment and it starts to get that, it can switch to a higher quality stream. So like on the illustration here, after the first 10 seconds, it will actually switch to the mid quality stream because it noticed that the network is fast enough. I can download these chunks. And then it continues with the mid quality stream for 2 segments. And then it notices that actually the network is so fast that I can actually switch to the high quality stream. Now, as it is playing the high quality stream at certain points in time, it may be that the network is congested, so it starts to take a longer time to download these video segments. And then again, the player will monitor for each segment it downloads, how long it takes to download the segment, and make a decision itself when to switch to a lower or higher quality, hence the name adaptive streaming. The actual criteria for when to switch between lower and higher quality streams is not defined by the adaptive stream protocol itself, but that's up to the player implementation and configuration. So it can depend on the end user device when it actually switches between these qualities. So that's a very short introduction on how the adaptive video bit rates work and why is this important. Well, let's look at the next slide. So here I have actually taken a real world situation. I'm myself watching House of Dragons first episode. In the upper figure, I'm watching it from home, and in my home we have roughly 30-40 megabits per second downlink stream, depending on the quality. It's over a 4G network. And in the lower graph, I'm watching the same episode from work, of course, non-office hours. To watch this video, and then I record and look at analyze the packets to see what the stream looks like in that case. In this case, we can see that actually, as we know, that in my home I will get a HD quality because I'm watching from a smaller screen. The HD quality will be enough, and in the office I have a bigger screen, so I actually have the full HD quality. And the bit streams are something like 2.4 megabits per second for the HD quality and 3.9 for the full HD quality stream. But it's not an equal stream sending 4 megabits per second all the time. It's rather microbursts. From home we can see that because my connection has lower capacity, it takes some 400 to 500 milliseconds for each segment to download whenever the player gets the next segment to play. And in the lower figure chart, because in the office we have a faster connection, actually it takes only 100, sometimes 200 milliseconds to download. So it is much shorter, and also we can see that the spike is much higher. So I do get a download speed of 160 megabits in the office, and then at home something like 26, 27 megabits per second at best. And again, why is this important? That's the nature of TCP, is trying to get as much capacity from the network as possible, or quick protocol nowadays. In some cases the players will use also the quick protocol for the download. Well, the interesting part comes when we start to look at how this will look in the transport network. How does it look when I aggregate multiple viewers watching, for instance, House of Dragon or any other streaming video? So let's look at the next slide. So here I have simulated what it looks like on the chart above when I have 189 viewers watching the House of Dragons. The reason why I have exactly 189 viewers is that I wanted to reach an average of 400 megabits per second on the link. And of course, each viewer will start watching the stream at different points in time. So these micro bursts that I had on the previous slide, they will happen at different points in time for each of the viewers. And when we aggregate these flows together, this is the sum of all of those flows. As we can see, it is fairly spiky. Also, this aggregate flow, we get bursts at maybe something like 65% above the average in this particular case. I have 1 minute example here. The scale is one minute here for the view. But when we look at the below chart, we can see that when we have a much higher download link for the viewer, then the aggregate traffic will also get much more bursty. So in fact, the bursts here can be as big as 200% above the average. So my average is 400 megabits. At times I can go up to 1.2 gigabits per second in these micro bursts of these aggregate flows. So this means that if I would have in my transport network, for instance, a 1 gig, I would already start to see significant delays when these microbursts happen, because I have only 1 gig capacity. So that means my buffers will start to fill up, and some of the packets have to wait, which then introduces latency in the network. The video itself is not necessarily too sensitive to the delays, but I have a lot of other traffic in the network, video conferencing calls, voice calls, in the future, much more control traffic, which is very much delay sensitive. So these types of traffics will start to suffer when we have these spikes. So it means the point here being that when we look at the average utilization is same in these both scenarios, but a decision on when should I be concerned and start planning to upgrade my capacity in the network cannot be made based on the utilization figures. That's what I'm trying to show here. It really depends on how much downlink capacity each viewer has. The bigger capacity, the larger the bursts of the traffic in your network. Now, on this slide, I looked at the 1 gig link, so it's a fairly small capacity in today's network. So let's do the same idea for a 10 gig link. What will these aggregate flows look like? So on the next slide, I have the same situation. Above, I have 1,890 viewers watching House of Dragons with a downlink speed of 30 megabits for each of the viewers. As we can see here, the traffic is not as bursty anymore as with the 1 gig link. So here I have a 40% utilization as well, 4 gigs on average of traffic, and then I will have a burst of something like 25% above this average capacity. In the chart below, we can see similar thing for when we have the full HD viewers with fast download links. I have the same average amount of traffic, which would be 1,015 viewers. We can see here also that the bursts are much lower than in the 1 gig case. It's 65% above the average, but we can see also that it is still very much burstier than in the case where we had much lower downlink speeds. So again, the same thing really applies when we have higher speed links. The traffic will still be much burstier if you have a very large downlink speed for the end users. So the final question for this exercise is then, of course, so roughly, if I'm thinking about that, how much traffic on average can I put on a 10 gig link before I should start to see performance degradations? So that's what I do on the next slide. Increase the number of, I see that I can increase it to something like 8 gigabits, or actually maybe even a little bit above. When I'm at 8 gigabits average utilization, the bursts will actually be even a little bit lower, because we have even more viewers and they are starting at random times, so they kind of cancel out. So we have only a 15% burst. So we are good with this 8 gigabits utilization. In this case, traffic will go up to something like 9.5 gigs. So we are well below the maximum capacity of the link, and everything is working smoothly. But if we look at again at the below picture, if the viewers have a 200 megabits downlink speed, then we can only load the link up to 6.5 gig utilization on average. Then we already, as we can see, we start to have issues. At some points in time, we start to have bursts that go up to the link capacity. And that's the point where you start to see the additional delays in the network. So as we can see, there it's a significant difference here between these two scenarios. If we have a lower downlink, I can load it up to 8 gigabits. If there's a higher downlink speed, I can only load it up to 6.5 gigs. And remember, in this scenario here, we are still just talking about 4G downlink speeds. And the point is then when you move to the 5G, the downlink speeds will even grow tenfold or more actually. So you can have up to 20 gigs of downlink capacity once you have the standalone networks. So that will make this traffic even more burstier. So you could not even load it up to the 6.5 gigabits in those scenarios. So let's summarize now this analysis of the adaptive streaming traffic. So as noted, the video is divided into short segments. So in my example there from Wowza, I had a 10-second segments. Like you maybe noticed from the charts when I was watching the House of Dragons, I found out that in that case, you can clearly see that there are spikes every 4 seconds on the wire. So that means that the video is segmented into 4-second segments. That's the trend to make them shorter and shorter, these segments and nowadays. And this adaptive streaming, it's not an even like if we know that an HD stream, for instance, is something like a 2 megabits, a little bit depending on what types of codecs, etc. are used. But it's not an even 2 megabits per second, but it's rather every 4 seconds or every 10 seconds, depending on my segment length. There will be very, very large microbursts up to the link, actually downlink capacity. So the higher the download speeds I have, the higher the bursts will be. And of course, also as we are looking at the trends today, so people want better and better quality video. We have better and better phones, better and better televisions. The better quality video, the more bits to transfer. So there's of course these higher quality videos will also make the bursts much larger. There's much more data to transfer. And the key point that I really want to bring out here is that now as we move to the 5G networks and looking at these very, very bursty traffic patterns that the video is causing, the average link utilization is no longer really useful to tell you if a link is congested. It depends so much on what type of traffic the user is looking at and how high this user's download speed is. That will affect how bursty the traffic is, and that will affect on when you should actually start to consider upgrading your links. You don't want to put too much capacity in your network upfront just to be on the safe side. You want to know where to invest and when to invest in which parts of the networks. Well, if the utilization is not really telling us the real situation, what is the way to monitor the 5G networks? What is the right way? So if we look at the traditional way with the bandwidth utilization, SNMP has been the way to monitor it. It has typically been 5-minute averages by polling counters from devices. And these kind of granularities will not be even near to be able to catch the microbursts. Of course, they are milliseconds long, not 5 minutes. So a 5-minute average will show that everything is fine, but you need to be able to characterize the microbursts, how bursty your traffic is. You could potentially go down to polling maybe every minute with some solutions, but it's not really technically feasible to poll every second or let alone to go to sub-second levels. The second alternative to look at is passive monitoring. Passive monitoring solutions out there today typically can monitor the microbursts, going to sub-second levels, looking at utilization, recording what the maximum utilization has been during these time intervals. But the problem with the passive monitoring solutions are that these probes, passive monitoring probes, are typically quite expensive. So you can deploy some probes centrally, but they don't really provide you the visibility to the transport links further out in the network. And that's actually where you really have the issues, as you maybe saw from the example with the 1 gig versus the 10 gig link. A 1 gig link will be much burstier than the 10 gig link, which can transport much more viewers. Different patterns will kind of cancel out when there's more viewers, so it's not as bursty. So that translates, of course, also to the central locations where you typically have 100 gig. That's not where you're going to have the biggest issues with the microbursts. You need to have visibility further out in the network, closer to the base stations, and how those transport links are really doing. So the solution that you need is really an active monitoring solution. The good thing with these active monitoring solutions are that you don't need to deploy new hardware all over the network in order to be able to get full visibility of the network. So you can put only a few centrally located probes, but they are still providing actually both an end-to-end view all the way to the base station, and also providing a segmented view, able to look at the performance of the intermediate devices as well. And how is that possible? Let's look at that on the next slide. Why it's possible is that the TWAMP protocol has been out there for a quite long time. It's an old standard. And nowadays, all the major network element vendors have implemented support for this TWAMP reflector in their devices. So both my base station will have inbuilt TWAMP reflection capabilities, regardless of which vendor I am using. And also my router devices in the network will have this reflector functionality as well. Maybe the only part where there might be a bit of lacking of this functionality are the radio links. So some of the radio links don't have the capability right today, but they definitely have it in the roadmap and are implementing it. So they will have it as well. And there are actually quite cost efficient smart SFP solutions that you can use in those cases to also get the capabilities for the radio links. And now the secret sauce is, because we have these reflection capabilities in all of the devices in the network, this central probe can send out the TWAMP packets to each of the intermediate routers along the path to the base station as well as to the base station. So we get the end-to-end view to the base station, and we also get the segmented view, because when I'm monitoring the quality to each of the intermediate routers, by looking at the measurements and deducing when I start to see bursts, I can then or my reporting solution can do analytics on this data and show me which segment in the network is actually congested. All of these measurements combined will provide me this segmented view between each of the devices in the network. I thought also I would show how this looks like in a real world situation, so that you get a feel for it. In addition to the measuring functionality, you of course also need a management solution, a reporting solution that's able to do all of the analytics on the data and show you where in the network you have the congestions. And this is from one of the proof of concepts that we did with one of our mobile customers. They actually had a pretty good network, but we're still seeing issues in the network. And we actually found out what was the issue. If you look at these two charts, so on the above chart, I show the average delays measured towards a certain base station. And this actually kind of illustrate the same thing as that bandwidth utilization is not really going to tell you about the real situation. When you average the delay over a measurement period, these microbursts cancel out. So you actually don't see that you have any issues at all. It looks very nice. I have a 3 millisecond stable delay, a little bit of bumps somewhere, but I would not be concerned at all looking at the above chart. So in addition to this normal average KPIs from the reporting solution, you also need the capabilities from that reporting solution to show you burst KPIs. So the below chart actually shows the same base station in the same time frame, but showing the burst KPIs, and that gives a very different picture. So you see these light blue spikes that we have there. Those are actually showing when I am experiencing these microbursts. And as we can see, for the case of this particular base station, I'm actually having it fairly frequently, and it seems in this particular case it's close to some homes, so people are watching videos in the night, and that's causing a lot of strain on the network. So it starts to spike then around nighttime or evening time when people are watching a lot of videos. And the good point here, when we, in this case, because we are starting to see these microbursts, at this point, it's still not going to affect the average user. We can see the average delays are still quite stable. You can see there's a few small bumps here and there, but nothing to be worried about. But as we can see, some of the users are still experiencing momentarily 20 milliseconds, almost 20 milliseconds additional delay because of these microbursts. And as the traffic increases, these microbursts will also increase. And if you are not adding capacity, at some point you are going to start to see also packet losses, because these microbursts fill up your buffers in the routers, in the network, and then they can't hold any more packets, and they start to drop the packets. And that's when your service will degrade dramatically. This kind of burst, the tools to show the bursts in the network will actually give you time to react before the end users actually start to see really bad service. That is the point of this chart. In addition, I just want to summarize a bit what sort of capabilities you need from a modern 5G performance management solution. So I think the first point was really from the previous slides, you need a full visibility into what's happening in the network. As you saw from my charts, also from real-world situations, you don't necessarily see these microbursts, these momentary degradations in performance in your network with the traditional tools that are out there today. And actually, Heavy Reading has done a study and found that 98% of the network issues are invisible to the operator. So there's a lot of issues there, like these microbursts that are affecting the services. The operator is not aware of these issues, but the end users or some of the end users will definitely be aware of them. So you need to have the full visibility. You need to have a solution that can monitor all the parts and devices in the network, and also show you both the end-to-end view and the segmented view, so that you know where you have these congestions and congested links. Now that's the core of the thing, because that also then provides you the fast time to resolution. So you need to have the tools that can identify where you have the issues and where the root causes of your issues are. So typically 80% of the time is in the data networks. They are so complex today that you spend 80% of the time typically doing the root cause analysis. And then once you know where the issue is, and it only takes the remaining 20% to fix those issues. But the dynamic nature and the complexity of the data networks has dramatically increased the time of troubleshooting. But as the kind of mode of operation that you want to target is, of course, to go towards a proactive approach. So rather than putting time on fixing existing issues and doing it as quickly as possible, which you, of course, want to do, ultimately, you want to get into a state where you as much as possible fix issues before they are actually happening to the end users. And that's what you can do with this sort of microburst detection capabilities. You can react before you can find the sites in your network that are becoming congested, and then you can upgrade the capacity in time before the end users are affected. Key also is the accuracy and granularity So with the demands of some of the new services that will be on the 5G networks, you need really exact measurements down to the microsecond level to meet requirements of the ultra reliable low latency services. And to catch the microbursts, you also need very granular measurements that can send out packets up to 100 packets per second, so that you are able to properly catch the microburst in your network. A very important point to also look at is the multi-vendor support. As I noted earlier, you do want to have the end-to-end view down to the base station, but you also want to monitor the intermediate devices in the network. It's very rare that you have bought all of your devices from a single vendor. In many cases, you even buy the base stations from different vendors, and typically you will select a different vendor for the routers and the transport network compared to the base station vendors. So you have multiple vendors in your network, and you need to have a performance management solution that can monitor to all of these different vendors that you have in the network. And finally, final point, which is very important, is it's important to have a good performance management solution with all of the reports, etc., that helps you operate your network. But you have a lot of existing solutions, and you are potentially using this data for a wider scene to integrate with other data in your AI ML analysis tools. So you need to be able to also export this data, not introduce isolated data lake into your OSS environment, but get this very valuable data into your other OSS systems, so that you can enrich your other reports as well with this data. And of course, today automation is very much on the top of everybody's mind. You also want to automate all of the measurements, the configuration of the system. So you also need the APIs to be able to automate configurations of measurements and so forth. So one of the solutions out there is the PULSure solution from Creanord. It's really state-of-the-art modern monitoring for 5G networks. We actually have capabilities already, which makes you future-proof also when you will upgrade to the 6G technologies and so forth. In addition to the active performance monitoring that we talked about today, this solution also includes service activation testing, which nowadays is becoming more and more important. Again, related to this proactive approach, you don't want to put new sites live and find out immediately that you have issues. You rather want to run a service activation test to make sure you remove any potential issues before you go live. And also full and automated SLA reporting. That again is of course very important for the 5G networks as you move to monetize on the 5G network and you introduce more business services. The SLAs are very important in those cases. So they are all available from this PULSure solution. And we have a full range of both physical, virtual, and containerized probes. So we are ready for all of the different types of operations and scalable from very small networks to very large networks. And perhaps most important of all, we are interoperable with all of the major network element vendors. So it's very cost efficient to deploy. You deploy a few of our probes, 4 or 5 of the probes, and you have visibility to your full mobile network, and you have a multi-vendor view without doing any sorts of additional integrations, except of course integrating our data with the rest of your OSS environment, but you don't need to integrate with EMS systems, etc., to get this multi-vendor view. So it's a very nice and recommended way for 5G performance monitoring. Okay, that's all I have time for today. I hope this was interesting for you. We are at Mobile World Congress, so if you are going there, please come and meet us. We are in Hall 7 at the Finland Pavilion. Check out our web pages. We have several on-demand webinars, blogs, and so forth about multiple topics. If you have any further questions on this presentation or some other related questions, please send them out to me. You see my email contact information at the bottom of this slide. Thanks everyone for participating, and I hope to see you in Barcelona.